Good morning. Welcome to our final design review. We are Team Melpomene, and we'd like to introduce you to Project Fire. On our agenda, we have first, our introduction and our problem space. Second, our technical overview involving our systems, mechanical, electrical, and software. Third, our closing remarks, including our risk assessment and our conclusion. Introduction and problem space. Most automatic fire sprinklers activate at a ceiling temperature of 170 degrees Fahrenheit. At 15 gallons per minute, these sprinklers pump a ridiculous amount of water into the environment, dousing every nearby object with stagnant brackish water. This water sits in pipes and does not get flushed. In the event of a small fire, they stay inert until a fire has spread through the room, and when activated, they stay on until manually turned off by the fire department. This means that once a fire spreads, it will not stop spreading until your entire room is destroyed, regardless of your current fire sprinklers. This is simply unacceptable for high-risk areas. In cleared rooms or art museums, a single fire can wipe out priceless artifacts. If not by fire, then by water. One set-off of your sprinkler system means the entire area of electronics or sensitive, valuable items can be ruined. Our solution uses an intelligently aimed nozzle to put out small fires before they can spread. Next, we'll get to our key requirements. For our terminology, a fire is referred to any surface area equal to or greater than 6 inches by 6 inches occupied by a Class A fire. This means a wood fire or a paper fire and not, say, a grease fire or an electrical fire. We chose this because it is 30% larger than most commonly available laboratory burners. Requirements. It must operate autonomously. It is capable of deploying an extinguishing system to a fire within 30 seconds of detection. 30 seconds is all it takes for a fire to go from a spot fire to a room fire in dry conditions. We aim to prevent these before they happen. We want a 10-year product lifespan, which is long enough for your sprinkler to be installed and work effectively before it fails. Next, a radial range of 10 feet, which is the same as contemporary fire suppression systems, and one that mounts to the interface of a current automatic fire sprinkler system. Now, past our requirements, what defines our product? First of all, it's autonomous. No human input is needed for it to function. Second, it's ceiling mounted. This allows it to hit every part of the room that is not covered by existing surfaces. Third, it is supplemental to existing suppression systems. A standard fire sprinkler will go off at a ceiling temperature of 400 degrees Fahrenheit. Your whole room is on fire already. These are mandated to be installed in every home and commercial setting, and by the time they're set off, the entire room is ablaze. Our next feature is that we're decentralized. The system works just as well with one unit as it does 5 or 10 and does not cost any additional dollars to set up in small quantities versus large. Next, it's easy to install. All it takes is to screw in one pipe, plug in a wire, and set one value on a computer, and your device and solution is ready to go. Finally, it's sleek. It looks perfectly at home alongside any other device you have installed in your ceiling, from lights to cameras. Now, onto the technical details.
We'll be going over a general overview of the mechanical parts of our product. First, on the right is a render of our product. This is what a consumer would receive when ordering our product with this appearance. If we consider our product as just a bit of a black box, there are only a few things to consider. With our design, the height of the ceiling doesn't really matter. As long as the nozzle sticks out of the ceiling, our product will work. Our product only depends on the building piping, and as a result, may have a different length protruding depending on the space in which it is installed. This non-reliance on the ceiling also makes installation a breeze and requires minimal changes to existing infrastructure. However, depending on this height, it does affect the effective range of our product, which we'll detail later. From an outward appearance, a camera and an IR sensor get information of where a fire is, as you can see below, and the nozzle gets pointed towards the fire. After that, the water gets sprayed and the fire gets put out. We made the outer housing transparent now, and we can really see the systems that make this happen. We have 4 main mechanical subsystems. The first is the structural frame, which provides mounting points and structure for the rest of our systems. The second is the outer housing, which provides primarily outer aesthetic, as well as a couple of auxiliary functions. Third is the water delivery subsystem, which is concerned with getting the water from the piping in the roof into our system and out of the nozzle pointed at the fire. It is also concerned with making sure no water gets out when there isn't a fire. Lastly, our Gimbal Mechanism subsystem acts to aim the nozzle quickly and accurately at our fire, given the data from our sensors. The first subsystem we will be going over is the structural frame. From this frame, we require a couple things. First of all, it had to be able to act as a mounting point for every other thing in our product. As you can see on the right, our only real attachment point is the pipe threading into the building's piping. As a result, we needed a frame that could transfer all the loads in our system to this pipe. We also had a few other requirements on top of this. First, we required this to be relatively cheap and easy to manufacture. It also needed to provide mounting points to attach our electronics to. Furthermore, we wanted our system to be able to install really easily into existing infrastructure. We can divide our structural frame into two main parts. First is the mounting plate. This is made from bending, cutting, and punching a 1/8 inch thick steel piece of stainless steel. By choosing a bent sheet metal instead of machining or casting, this drastically reduces our costs while still meeting our requirements. We can add simple through holes to this plate to provide mounting for the PCB and motor. The through holes can be used with nuts and bolts to create rigid connections wherever we need. We also added hemmed edges to our bent sheet metal, which provides additional structural rigidity at very little cost. The second part is the threaded pipe. As you can see on the right, there's a threaded pipe. On the threaded pipe is our mounting plate, and on either side of it is a nut. There is also an outer housing in there, but that'll be detailed more later. By using this threaded pipe and nut, we give ourselves a very simple way of installing our system into existing infrastructure. Current piping already has T-joints, and we can just screw our product right in. That means we can pre-assemble everything in a factory and make on-site installation as minimal as possible. Furthermore, this gives us a rigid attachment point without having to mess with the water infrastructure or the ceiling in any way.
Okay, so now that we've talked about the frame, we're going to talk about the outer housing, which is my contribution. All right, so our housing requirements, mainly our motivation behind our housing was that we wanted to simplify our inputs and our outputs going in through our unit. Essentially creating a shelter that creates a black box around our components. So we just have power coming in, we have visual through our camera, we have IR info from our IR sensor, we have supply water coming in through the top, through that threaded pipe, and then airflow is going in and out through the vents in the top and bottom of the unit. And then our main output that we're just trying to get is that water stream that's trying to target our fire. Additionally, some other requirements is that we wanted to have a place to mount our camera from that was relatively low so that we could optimize our field of vision. And then we also wanted a little bit of structural rigidity and thermal insulation. Note that it's not highly significant. It's not taking the significant loads that our internal components are going to be facing. As Johnny discussed, we have a frame to mainly take those loads. This is mainly just protecting the components from something that might knock into it or anything, any debris that might otherwise interfere with the components. As well, we also wanted to improve the cosmetic appearance of the unit. So, yeah, as I mentioned, we wanted to shield our internal components, support our camera, and facilitate cable management. So our material that we ended up choosing for this was injection molded plastic because it's cheap and easy to mass manufacture, especially with the relatively more complicated geometries that we wanted, such as like the cable management rails and the air vents that you can see there. as I mentioned before, we decided to go with a non-structural housing since we have a structural frame instead. We just wanted our structural components to be relatively small to reduce our weight. And we thought it would be much more appealing to have a plastic housing that would just shelter the components from any kind of tampering and making it more aesthetically pleasing. The top plate of the housing is secured to the frame via two 8x32 screws and nuts, which you can kind of see on either side of the threaded pipe here, as well as the clamping nuts that are on top of the bottom of this plate. The housing was sized so that all of the components have at least ½ an inch of clearance, so there shouldn't be any issues with fitting it or assembling it. Additionally, we have the camera, which is mounted here at the bottom, and it's at the bottom just so that there aren't any other components obstructing its field of view. And then we have these internal rails along the sides here. There's two of them, and they will be managing the cables going from the PCB to our actuating components and our sensing components. And that's just so that the cables don't get caught up as the mechanism actuates. Additionally, we have these airflow vents that I mentioned on top and bottom, and that is just to prevent the accumulation of humidity, which would be bad for our system because it might increase the risk of electronic failure, which we don't want, of course.
Hello, my name is Odalys Sanchez, and I will be presenting Subsystem 3, the water delivery. Our assembly's method of water delivery is outlined in this schematic. As you can see, the mechanism will use the installation site's existing water supply as the primary source of water. The solenoid valve is activated by software, which will then ensure that water is diverted into the mechanism. When the solenoid valve is not active, water will flow past the mechanism through the building's pipes, ensuring it does not stagnate in a reservoir behind the mechanism, as existing sprinklers water supplies do. When the water travels through the tubing, it will exit the nozzle and spray at the fire that has been detected by our system. To select our valve, we looked through 3 primary categories of actuation: solenoid, motor-driven, and air/hydraulic. We also took into consideration 3 important characteristics and their impact on the system, as well as our valve selection: pipe size, material, and the minimum pressure to operate. We also had some requirements, such as 10+ years of durability, heat resistance, corrosion resistance, and sufficient flow rate for our purposes. In the end, we chose solenoid as it proved to be the best for our applications, primarily for price reasons. The following are the solenoids that we chose, both for our final product and for the cheaper prototyping. Though both would serve the purpose, it is recommended that the cheaper option is used, primarily for price purposes. The following chart outlines the price versus characteristics of each solenoid valve, comparing whether a higher price valve would actually be better than simply sticking to a lower price valve. In the end, there are some trade-offs, but a lower price valve would not be significantly lower in durability than the higher priced valve. Another aspect of water delivery is the tubing and leaks. It is important to prevent any leaks from escaping from our tubing, and in order to prevent this, we will employ standard plumbing practice of applying PTFE plumber's tape and or pipe joint compound around any threaded connections. This will ensure no leaks form at these threaded joints. To fit the tubing to our system, there are various requirements that we have taken into consideration in our choice for fittings. They must be durable for 10 or more years, able to sustain low to moderate pressure, be compatible with flexible tubing, and cost-effective. In these diagrams are the various options we were presented with. We ultimately chose, based on this broad range, 2 primary fittings that would be used: barbed fittings or compression fittings. The pros and cons of each type of fitting were outlined in this table, and upon consideration, we decided to use barbed fittings. The main advantage of compression fittings is the ability to support higher pressures. However, our mechanism does not use very high pressures, and so for our purposes, barbed fittings would suffice. In order to ensure that the material does not corrode, we also would like brass for our final product fittings. Aluminum is more expensive, and the only advantage over brass is that it is lightweight. Steel is significantly more expensive, and it does have its advantages, but it's negligible unless in a high corrosion or high temperature environment. As before, we took into consideration the various aspects of our system that would define our choice of nozzle, primarily corrosion resistance, a far reach, in other words, the ability to travel across a long distance for the spray, a strong penetration of fire, in other words, a dense flow of water, not mist, and as the area does not need to be cooled, ideally fire would be put out before it spreads, which also affects how the shape of the stream will come out, as various streams are designed to cool the area rather than putting out the fire. With these considerations in mind, we also decided that our nozzle would be made of brass, as it also is cost-effective and will provide corrosion resistance. A solid stream nozzle will provide greater reach and penetration than a straight stream, and to ensure a consistent reach that will reach the fire detected by the algorithm, a constant pressure nozzle will be used. Under these specifications, a one-piece brass smooth-bore nozzle fits our design constraints.
Subsystem 4, Gimbal Mechanism. For mechanism selection, we selected 5 different types of gimbal mechanism to do the comparison. Each of them have unique method to provide gimbal motion using 2 motors. We are looking for from the mechanism should be able to rotate 55 degrees in both yaw and pitch. Smooth rotation with minimum motors. Low parts count. Low weight. Easy fabrication. Simple integration if needed. Here is the list of mechanisms that we have selected. Mechanism 1 uses 2 motors to provide gimbal motion. Mechanism 2 also uses 2 motors to provide gimbal motion. Mechanism 3 uses motors in series, which means that 1 motor is on the base and the 1 motor is on the rotating arm. And mechanism 4 uses 2 motor and also gearings to change the direction of the motor input. Mechanism 5 uses 2 levers to control the rotation of the gimbal mechanism. To better compare the mechanisms and find the one that we needed, we listed the properties that we are looking for from the mechanism. from part count, easy of fabrication, rotation 90 degree, integration, stability, programming, and we listed total with different weights to it. And here we have found that Mechanisms 3 has best fit for our project. Mechanism operation range. The camera that we have selected has 90-degree viewing angle, which means that our nozzle should have a maximum moving range of 45 degrees from the vertical line. In a room where the camera is mounted 10 feet above the ground, the operation range should be 400 feet square. During the operation, the nozzle will rotate 50 degrees in both yaw and pitch. The distance between two fittings will change due to the rotation. The tube lengths need to be corrected to tolerate the maximum movement angle of the nozzle. A slackness to the tube can resolve the problem. Several points need to be considered during the calculation. Distance between two tips of the two fittings, radius of the tube fitting, and bending radius of the tube. Here is the simple calculation that I have done, and it turns out we only need 5.59 inches of the tube to tolerate the distance change between two fittings.
So moving on to motor selection, the first step of selecting motor is selecting the type of motor. So we started with stepper motors because they're precision oriented, and for our mechanism to work correctly, they need to aim very precisely. However, stepper motors requires motor controllers, which would take up extra space in our mechanism as well as add additional cost. As for stepper motors as well, they're more suited for open loop control, and they also will lose orientation if a step is missed. So stepper motors get their position from the steps that they're taking. And so it knows, for example, how many steps it needs to take to get to the next position. However, if something is holding onto it and it takes a step, but it's being blocked by something, it will just forever be one step off after that, which is not what we want. It'd be hard to know the positioning of the motor. Another big issue with stepper motors is that it's constrained by the step resolution. So for most stepper motors of this size, the step resolution is about 1.8 degrees. However, based off of our definition of kind of the range that range of the sprinkler, which is a 10-foot radius, and the definition of a fire in our case, which is 6" by 6". The resolution that we would require from a stepper motor would be below 1.4 degrees. So that falls just below the 1.8 degree stepper motors that are commonly found. And that's an issue because to be able to precise enough for our usage, we would have to add gears or spend more money for a more precise stepper motor. So instead, we went with servos because they have better position control, better speed control, as well as better torque control. They operate on a closed feedback loop, and most importantly, they're not constrained by a step resolution, and they do not require a motor controller. So the motor selection criteria, moving on from that, these are the big ones. So the first one is the most important. It is the torque requirement. The torque required comes from the weight of the mechanism itself, as well as the weight of the motor, because there is a second motor that moves along with the mechanism as the nozzle aims. Another weight we have to consider is the weight of the water inside the flexible tube before it's ejected, as well as the pressure from the water ejecting, from when the water is ejecting and it's pushing back onto the mechanism. The size is an important criteria as well because the length of the motor cannot be longer than the radius of the housing. And the weight is important, as we talked about earlier, because it increases the amount of torque required. The cost, we're aiming for about below $200 per unit. The reliability is very important for this because this is a mechanism that will kind of sit and use potentially for decades before actuation. And when it needs to be actuated, it really needs to work on demand because it's a matter of putting out a fire or not putting out a fire. As for water resistance as well, because these motors are sitting kind of close to water, they should be water resistant. However, this can be handled by motor housing. So we're not looking for a more expensive motor that can handle water resistance. So the motor selection process comes from, the first step is kind of picking out feasible motors based off of just a general look at the sizing, as well as the torque range. And then from there, if it seems feasible, then the torque needed is calculated. And this is different for every motor because of the second motor that is sitting on the mechanism that is moving. So when the mass and the weight of the motor goes up, the torque needed to move the whole mechanism goes up as well. And some other criteria that's considered are cost and mass. And so this chart here is a weighted chart. So the mass and the torque and the price are all given a weight, and then each motor is assigned values. And as we can see, the motor with the highest value at the end is motor number 9. So this is the motor selected. It's a very small, it's a very small motor. As we can see, the diameter is 26 millimeters, and the length is only 22 millimeters. So it sits very nicely within our mechanism. Some of the important specs about it are its torque, its maximum torque, which is enough for the to operate the mechanism and hold up its own weight. It has its operating temperature range fits within the operating temperature range of the whole system, and it weighs 25 grams, which is really light and doesn't weigh down our whole mechanism as well. So for motor mounting, the motor is now, instead of being mounted to a motor mount and then to the mounting plate itself, it's now just directly mounted to the mounting plate. The mounting plate has been moved up to kind of against the mechanism, and then the motor is attached just behind that. So we've got one less moving part. Also helps with the assembly so that we don't have to slide the motor into any closed mounts, and then the wiring will be easier as well. Also moving the whole mounting plate closer also puts less strain on the plate itself. However, the screws will need to be a bit longer now because it has to go through the mechanism and the sheet metal and then into the motor. Our motors are mounted direct drive as well. We don't have gears because the gears will just add more weight and we'll have to make more space for it inside the housing. A lack of gear will also reduce backlash, but most importantly, it is less points of failure because this mechanism is just being stored kind of without movement for decades before actuation, and we just cannot have one of the gears fail for some reason through when it's being stored, and then for that to amount to a failure on actuation when it needs to.
Now we move on to the fasteners that I have selected. So for our housing, we have quarter 20 screws and nuts. We have 4 of them that are just equally spaced apart radially. And that's just gonna secure the top plate of our housing to the lower part of our housing. These were deemed to be like non-critical. So we just wanted to make sure that we had something that was like cosmetically appropriate, and that definitely wouldn't fail, which was pretty much any size screw. So we didn't put a whole lot of engineering labor into that, as we had other engineering challenges that required more labor. And then as well, for securing the top plate to the frame, we used 832 screws and nuts. So we used 2 of those, and that's just to, again, provide a little bit more of a connection between the structural component and the top plate of our housing, just so it's extra secure. We were particularly concerned about this when discussing the installation of the unit, which I'll talk about a little bit later. But essentially, we wanted to make sure that there wasn't any risk of the housing sliding in relation to these clamping nuts. So in addition to the friction provided by the clamping nuts, we also have these screws that are going to secure it to the frame, providing a little bit extra torque when we ultimately screw this whole unit into the supply pipe. Okay, so now we have our PCB fasteners. This was pretty standard. We just went with 832 screws and standoffs and nuts, just kind of modeled after standard industry practice. Again, this isn't taking any significant loads, so not a whole lot of engineering labor going into this, mainly just making sure they're an appropriate size relative to the PCB thickness and the sheet metal thickness. Now we have our exploded views and assembly procedures. So here you can see an animation of every single component in our system being assembled into first subsystems, and then those subsystems being assembled together. So the main subsystems of note here, I've put in bold in the assembly instructions, mainly the nozzle subassembly, which you can see in this lower left, the mechanism subassembly, which you can see just above it, and then the solenoid assembly, which is right here. And so those subassemblies get assembled separately, and then they eventually all coalesce. I won't get too much into the details here, but we've made sure that all the steps to properly assemble subassemblies are correct, and then going in a logical order of how can we assemble the components in a way that they won't interfere with each other, and that we can make a unit that has ease of manufacturing. I'm going to discuss a little bit more in the later slides, the subassemblies. So here we have our nozzle subassembly, which is just our nozzle, our inner shell, and our IR sensor. So all of this gets assembled together, as you can see in our GIF, and then it gets assembled to the mechanism, which is also a subassembly that gets put together. Here's our mechanism subassembly. It consists of 6 pieces. So that will go together. Then these 2 subassemblies will join, the mechanism and the nozzle. And then we have our solenoid assembly, which is essentially just a sort of long pipe. So that gets assembled, that's 4 pieces. And then we have our, what I'm calling our internal subassembly, which is mainly just these 3 pieces here, the PCB, the frame, and the top plate. And then a whole bunch of fasteners, and then our internal components are able to mount to that. And then we have our external subassembly here, which consists of our housing, and our camera, and our fasteners.
So for our microcontroller, we selected the RP2040, and the requirements that this component meets is that it's able to fully control the operation of motors, the solenoid, the IR sensor, camera, LEDs, and speakers. Basically, how it does this is it sends signals to these peripherals through its GPIO pins. Basically, its input and output pins. And this is the main microcontroller in the Raspberry Pi, which will be used in the prototype. So at first, we were actually going to go with the Raspberry Pi Zero W itself. Yes, we are using it in the prototype, but we're also going to use it in the final product. But we realized that it has aspects that are not directly relevant to our final product. For example, like There's GPIO pins that aren't being used. There's also a Wi-Fi connection, which is something that we don't need. But it is excellent for prototyping and experimenting with. So that is why we're going to be using it for testing. And so for our sensors, we decided to go with the Raspberry Pi camera module, as well as the IR sensor. And so the requirements that it meets is that it is able to gather enough visual as well as thermal data in order for our fire detection algorithm to work accurately. And the alternative was to only use the camera to supply visual data to our algorithm. But we realized that without the IR sensor, the algorithm might mistake of a fake fire for a real one. For example, if it's on a TV screen, there's a picture of a fire, it might think that that's an actual fire. And so with the help of the IR sensor, the algorithm will be able to confirm if it is an actual fire through its thermal characteristics. So for our motor, this is going to be our design. And we basically have an external 5-volt supply powering these motors, as well as an input signal from the microcontroller. The requirements that it meets is that it has enough power for both motors, and it also allows a signal to come in to control these motors. At first, we were just going to use the 5-volt power from the microcontroller, but when we tested this with the prototype, the motors were not able to rotate at its full capacity. So for our solenoid, this is our circuit design. It's composed of external 12-volt power supply with the solenoid itself, and across the solenoid in parallel is a reverse bias diode, and as well as a transistor and a signal going through the 330 ohm resistor. The requirements that this satisfies is that it will able to provide enough power to quickly open and close the solenoid without much delay. And it allows a signal to come from the microcontroller to control the opening and closing of the solenoid. It also prevents voltage leaks, and that is due to the diode. At first, we were just going to use an external 5-volt supply instead of a 12-volt supply because this minimizes our power consumption, which we don't want to be too high. And it also eliminates the need to convert the 12 volts to the 5 volts. But this significantly reduces the opening and closing speed of the solenoid. And this information is given by the creators of the solenoid. And for our PCB, instead of putting it on a perf board or on a breadboard, we decided to go with the PCB because, for example, it significantly lowers the purchase cost of the microcontroller because we won't be going with the Raspberry Pi, but instead all we need is the microcontroller chip itself. And of course, we need to have the decoupling capacitors as well as other components. But those components are relatively cheap compared to the entire Raspberry Pi Zero. It's also smaller dimensions because there's no wires sticking out or anything. It is easier to produce. It is easier to customize, as well as the assembly is a lot easier now because it can be produced at a factory. Disadvantage is that it is hard to debug, and it must be designed and outsourced. And if something fails in the PCB, then it's very difficult to fix. And it's very difficult to isolate the components that need the repair. And so ultimately, we decided to go with the PCB because in the long term, it is more cost effective and it's more advantageous to have components with a low profile rather than like sticking out wires and complicated tangled wiring. For our power supply, we decided to go with the 12-volt 2-amp power adapter. This basically converts the AC voltage coming from the building into a usable DC voltage to power the rest of the electronics in our fire sprinkler. And to the right, those are the calculations. that helped us to come to this conclusion. And here's a flow chart of how our voltage is going to flow. So the power supply is on the left, and basically there's components. There's actually one component that needs 12 volts, and that's the solenoid. And then it'll go through a buck converter, which will convert the 12 volts to the 5 volts. And as you can see here, the motors and fire sensor requires those 5 volts. And inside the PCB, we're going to have an internal 5 volt to 3.3 volt converter, which will not only power the microcontroller, but also the speakers, the LEDs, and the camera. And here is the design of the internal 5 volt to 3.3 volt converter. And this successfully converts the 5 volt to 3.3 converter in order to power the microcontroller, speakers, LED, and camera. And this is inspired by a design that has already been solved by the makers of the microcontroller. And I also want to show the PCB design of not only the 5 volt to 3.3 volt converter, but also the decoupling capacitors, as well as flash of the microcontroller. And so as you can see here, this is the 5 volt to 3.3 volt converter, as we already showed. And as you can see here, this is going to be right here. This is going to be our oscillator. And right here, this is going to be our flash storage. And as you can see here, these are all the decoupling capacitors that are required. And yes, this will be provided to the PCB designers who we will outsource to.
As for the software technical overview, I'll start off with a data flow chart and the design overview. So basically what happens is the camera sends the visual data to our fire detection algorithm, which first converts it to HSV color space, then applies a pixel threshold, as well as dilation and contour detection. And then from that, we can create a bounding box around the largest contour. And in this case, it would be the fire in the image. And then these bounding box pixel coordinates, which consist of the X and Y, and then the width and the height of the box, are sent to the control algorithm, which then does a coordinate to angle conversion. And then there's an angle to PWM conversion. And then from this, the PWM signal is sent to the servos, which aim at the bounding box. And then the IR receiver is turned on, and we see if there is a high or a low. If it's high, that indicates that there is a large enough amount of IR radiation entering the IR receiver, and therefore the solenoid valve will actuate, and then the water will start flowing. If there isn't enough IR radiation, that indicates that this is not an actual fire, and then therefore it returns to idle, and then the PWM signal is sent to the servos to reset, and so then they reset to the idle state. So all the design choices have revolved around the following assumptions. Firstly, the fire detection algorithm side. So we have to reduce the excess cost through minimizing the false positives, and then put fires out reliably through minimizing false negatives of our model. So in order to do this, we measured a visual model accuracy with the MAP metric, requiring 90% accuracy. And then there's also verification of any detected visual fire with an IR sensor. And then the model can extract the location of the fire within 5 seconds. And then the model only detects orange and visible flames, so no butane and no blue fires, etc. As for the control algorithm, the nozzle targets a detected fire in frame, and then once it's verified, extinguishes it, and then it returns to idle once it's extinguished or upon no fire detection. And so we do this by converting the given bounding box coordinates into PWM signals to send to the servos for control, and then the LEDs also indicate the operation state for user interface. So as for the definition of success, we use the MAP metric for the fire algorithm as described below. And so you can kind of see how they calculate that. And so we used an intersection over union metric of 0.5. And basically this just measures how much of the detection is over the ground truth. And so we used a repository to calculate this across 319 images. So you can see, you can put the annotations here, the images here, describe your pixel coordinate format, as well as your own detections. And then from there, you can calculate what the MAP metric is with your model. And so firstly, I'll go over our detection model. So the visual detection algorithm breakdown is as such. So we do a conversion to HSV, and then we threshold the pixels between these values here. And then we segment the fires, and then use dilation and then contour detection. And therefore, we can create a bounding box around the largest fire in frame. And then we send those pixel coordinates to the control algorithm as described below. And here you can see a quick demonstration of that. So here's the contour and then the bounding box around it. So here's a quick comparison to some of the older detection algorithms that we had in the past. So this is an older one that's deprecated using a hard cascade. And as you can see, there's no detection at all for the fire here. And then there's actually an error in detection somewhere along the lines. Yeah, right there. And then moving on, here is our version using contour detection and dilation. So right off the bat, you can see that it detects it and then it changes as it goes along. As the fire grows, you can see the contours growing as well as the bounding box. So that's a quick demonstration of our algorithm. And so with this, we reached actually 91% accuracy on the data set as measured by the MAP metric. And so our data set consisted of 129 non-fire and then 190 fire images. And so we had 0 false negatives, which basically just means no missed fires. And then we had 13 false positives. So this indicates that while it has a high degree of accuracy, we still have a bit of a false positive problem. And so from this point, we realized that false positives needed to be addressed in another way, aside from purely visually, because our system does not differentiate between pixel colors that look like fires and then pixel colors that are actually fire. And so here I can show the results. So here's the 91% accuracy. And then here is the precision over recall curve that provided by the repository. So addressing the false positives, we came up with the idea of using an IR sensor actually attached to the nozzle. So basically, if the detection algorithm thinks it sees a fire, it will swivel the nozzle to aim at the box in frame. And so the IR sensor is attached to the nozzle to verify what the camera thinks is a fire. And basically, this just means that we have a secondary measure of detecting whether it's actually a fire or not, and it provides some verification for us. So the IR sensor must receive a constant stream of radiation, which indicates that there is actually a fire in the frame, and also it has to be for 3 to 4 seconds in order to verify. And this is basically to protect against remote controllers or any typical source of IR, because typical IR remote controllers emit a pulse for a short period of time, and this would basically allow us to not trigger our system in that case. And there's also a sensitivity adjustment potentiometer, which increases or decreases the IR radiation threshold needed to trigger the digital high for indicating that there's IR radiation within the sensor's range. So here I have an image of how we're actually attaching it on our prototype test bench here. So this is the IR on top of the nozzle. So we tested the system on the same data set using, again, which is 129 non-fire and then 190 fire images. And we got 0 false negatives and 0 false positives. So what this means is that the system correctly ignored non-fire images. It correctly swiveled to verify fire images were not real fires and reset to idle mode. And then the system correctly swiveled to verify that fire images were quote unquote real when we put a lighter in front of the IR sensor, which is to simulate a fire, and then it went into extinguish mode properly. And then lastly, it also ignored typical sources of IR, such as IR remote controllers. And there's a demonstration of this at the end. Moving on to the control algorithm, the first step was to normalize the pixel coordinates to an angle in the range between -45 and 45 degrees, since our image is a square. And so you can see our formula right here, pretty simple. Sorry, to go back a little bit, the resolution of our pictures or our images are 480 by 480 pixels, so it's a square image, and therefore we can normalize it by 45-degree angles and 90 degrees total. So then we convert those, we convert it to a PWM signal and then pass it to the servos. We can see down here the data flowchart. And so the servos will swivel and then verify for 3 seconds that IR radiation is constantly being emitted from that location. And if it's not constantly emitted, then that indicates that it's not a fire, and then the system will reset. But if it is a fire and that there is a constant IR radiation, then we actuate the solenoid valve and then extinguish by sweeping the area within the bounding box with the now actuated solenoid valve and the free-flowing water. So here's our prototype test bench. So all of our tests, as I referred to before, with the 0 false negatives and 0 false positives, we're done using this makeshift test bench. But there will be an improved prototype chassis for our final demonstration. So you can see here are electronics. Here's our Raspberry Pi, some of the other electronics up here for power, and then our actual gimbal mechanism is down here in the bottom left. Our camera is located here by the ribbon cable, and then our IR sensor and nozzle are down here, and the solenoid valve is up here with the tube extending from it. So here's a quick test bench demonstration. So we'll start off with just an image, and then you'll see that it will reset and go straight forward as indicated as it starts off once it realizes that it's not a fire. So if it's verifying now, realizes it's not a fire, and then goes back to normal. And then now we simulate that it is a fire with a lighter, and you'll see that it'll start to swivel, indicating that it's extinguishing. And then in our next test, we use a common source of IR, which is the remote controller, and I'll show it right here. So it sees the image of the fire, and then it's actuating the remote controller is actuating it, and you'll see that it goes back to the normal state once it realizes that it's not a constant stream of IR. And so that's pretty much the technical overview, as well as some more details of the software implementation for this project. Thank you.
And that brings us to our conclusion. If we look at our unit cost projections, we see that to be successful, the unit cost must be under $2,310 US. This takes into account the current fire incidence rate in industrial settings, as well as the effective radius of the unit and a myriad of other factors. Now, we can see if we look at our requirements versus our design outcomes, based on each criterion, that we meet or exceed every single one, besides one estimate. If we look at cost, we significantly lowered our cost from our success metric of about $2,300 to about $570 per unit. If we look at the operation method, it is fully autonomous. Additionally, we have a very low deployment time of 2 seconds, much lower than our necessary 30 seconds for success. We have to estimate that we have about a 10-year lifespan for the product, because more rigorous testing would be required to confirm this number. Our radial range was designed to be 10 feet and therefore is 10 feet exactly, and we do use existing infrastructure. Now we move on to some unknowns and concerns. First of all, our maximum operating range is defined by the camera field of view. We can improve our coverage by increasing this field of view on each camera, but that comes with a cost and complexity, and it is not worth the diminishing returns for the field of view increase. Additionally, optical detection systems are limited inherently. Fires that are not colored, such as ethanol fires, will be invisible to the system, and they cannot go past visual obstructions. These are known limitations present in any optical system. We also cannot say for sure that the lifespan of the final product is in fact 10 years. However, based on the components we used to design the final product, 10 years is a very reasonable estimate. The final concern is that we may actuate too often. We had some concerns that the fire system may actuate if the camera picks up anything that is not a fire that it might think is a fire. Due to our IR sensors, it will not spray the false positive. However, even actuating just slightly more than intended over the course of the entire lifespan may shorten that lifespan significantly. A broader surveillance for each room that triggers individual cameras could be a solution to this, but it would require much more time to integrate and design than we had. In summary, the final product design outcomes met our desired specifications. While there are some aspects of the system that could find optimization when designed for in manufacturing, we are confident that the current design solves the target problem space in a cost-efficient manner. As for acknowledgements, we'd like to thank our professors, Dr. Ankur Mehta and Dr. Jacob Rosen, for facilitating this design course and advising our design decisions. We thank our teaching assistants for their invaluable mentorship and guidance throughout the whole course. Finally, we'd like to thank our classmates for their thoughtful feedback regarding our design reviews. I would also like to give a special thanks to Dylan, Johnny, and Alex who worked on this project for their outstanding work ethic, invaluable contributions, and excellent quality of work on this effort. The entire team was integral, but these three really showed an extra layer of dedication to the project, and we couldn't have done it without them. Thank you very much.